Hi, this is Sandoval. Today we're going to be talking about estimating future water demand using population and water use per capita. So let's start from here. So the first thing that you should know is that, so basically, in this exercise, the objective of this exercise is to estimate the future water demand. How are we going to do this? Well, basically, first, we're going to estimate the population. And we're going to, basically, I'm going to teach you how to estimate future population based on historic records. So this is going to be the first part, estimating the population. Then the second part of this exercise will be about estimating the water use per capita. What we're going to estimate is how much water is used per person. And once we have done this, basically we have all the ingredients, all the required ingredients. So if we multiply the population times the water use per capita, where we are going to obtain is the future water demand. Okay, so this is pretty much the overall objective of this exercise. Okay, now when you are you're gonna receive two files. You're gonna be working with two files. So these two files are exercise 1 data and exercise 1 population and water demand. So here is the exercise 1 data, and here is the Word file for the description of this exercise. So right now I'm going to call it, I'm going to save this one as exercise 1 data Sandoval. Okay, so we're going to be throughout the course we're going to be talking, or we're going to be working with data related to Pájaro Valley and Watsonville. In this case, the future water demand that we're going to estimate is future water demand for a city located here in for a city called Watsonville, which is located between Santa Cruz and Monterey, in the Monterey Bay. This is the city. So we're going to be estimating the future water demand, municipal water demand for that city. How are we going to do this? Basically, what we will be doing is, let's start from here. This is data from the census since 1860 up to 2010 of what has been the population in this city. Let's start by creating a chart. So select these two columns, go here, and then what we're going to do is to create here in a scatter plot. Okay, so let's so this is basically what I'm asking you to do here. Then let me delete this one, and what I'm going to do is to, okay, so here actually we can actually, okay, let's add a name for this chart. So for series 1 here, I'm gonna put the series name that is going to be population. Okay, now once we're here, we are going to add let's add a trend line here. So you need to select and then right click, go to add a trend line, let's just here add. The previous one that I just did was add data labels, but we don't want that. We want add a trend line, and then go here, and you can see that there are many different trend lines that you can fit. So look, this is exponential. We can actually ask them to display this, the equation chart and the R-square value. So this is for exponential, linear, logarithmic, polynomial, power. Notice that power has the closest R-square value to 1. So this is 0.965. This was 963. So let's choose this one, power. Okay. So once we have done that, we're just going to, because we cannot see, the full equation, what I'm going to do is here, format of the trend, aligned label. I'm going to go here and select scientific with 4 decimal places, and it should look something like this, like this one that you're going to be seeing here. So as you can see, these are the same, and this one and this. Okay, so so the R value is about 0.965, which is very close to 1. So the X variable is the years, and the Y variable is the actually the populations. So here we're going to start creating using this equation that you have seen I copied here, and we're going to use this equation which comes from this regression to estimate what is the population according to this regression, to this equation. So in this case it's going to be, I'm going to type equal, open a parenthesis, 2.6401 times 10. This symbol you can obtain it by pressing Shift and 6. Then open another one to the minus 175, close the parentheses, times A6. And for A6 I'm just going to move with the arrows to select the cell that I want, which in this case is A6. Again, to the power of 54.292. Okay, so now we have that data, which basically what I was doing is just typing this equation. Okay, so we have the value that we were looking here is the value that we were looking here. Notice that in this I will be writing the equations, or you can actually see them here in this part, which is here where you can actually enter the equations. Well, now that we are here, let's copy this formula for the rest of the years, and you can type Ctrl+C and then select all these cells and type Ctrl+V. That's one way of copying it. The other one is that you just go select this. See how the cursor changes here? So it changes from this to this, and then you just drag it all the way down, or you can go here, and once the cursor has changed, you just double click and it will go all the way down. I mean, it is the same. There are 3 different ways of copying cells. Okay, so once we have done that, let's here in this cell, in cell 28, let's estimate the R square for this for these two series. What is the R square? Well, it's the coefficient of correlation. And what does that? Well, this coefficient of correlation basically it helps us to measure the strength of the association between two continuous or two variables. How close they are one to the other. That is, I mean, that's one way of actually estimating how good a regression is compared to how these two series are close to each other. As you can see, this line represents the regression and the points represent the actual population here. What we want to know is in a scale, well, how close they relate. The closer to one, the best. R can be this value. This one here, R squared, varies from pretty much -1, which it means that the two of them behave completely in the opposite way, to 0, where actually there is no correlation, no agreement between these two, to 1, which it will be a perfect correlation. The Pearson's R is also called the linear correlation coefficient, and basically measures the linear association between these two variables, how close they are. So in this case, let's type equal RSQ, and then we're going to select the last years, B, since 1970, for the population, that is the historic population, and how well this one compares to the one that we are estimating using our formula. So in this case, it's 0.9704, and this is for the last part. So as you can see, this is a correlation. Remember that the closer to one, the better. So well, okay, we have done this. Now let's do the following. Let's copy this and so this is one way of estimating the population. Now let me show you using a power correlation. Now I'm going to use a linear correlation. And basically what I'm going to do is the following. So I copy the previous, I just simply copy, Control-C, and then paste it here. And then what I'm going to do is to actually just try to take a closer look since 1970. So the first thing is that I'm going to here. I'm going to go only from 1970. So now we have this. So I just now selected from 1970 to 2010. And then the other thing that I'm going to do is just change this. Instead of being power, I'm gonna make it linear. Okay. So now we are here. As you can see here, this equation that we're seeing here, this regression equation to estimate using a linear regression, it's the one that we were that I was asking you here. Now, notice that in this case the correlation coefficient is 0.9915, which is actually greater than this one. Now let's go here and use this equation to populate since 1970 what will be the population using a linear regression. In this case I will type 939.82 times A17 minus 183.73 06.8. I'm just double checking this. Good. Okay. I'm going to do the same. I'm actually going to copy all of this for the rest of the time. So you can see the value that we were looking in the exercise here are the same values that we were asking here. I'm going to do the same. Actually, as you can see, I'm going to estimate also the correlation coefficient here in this cell, D28. How I can do? Well, equal RSQ, and what I want to know is what are these knowns, and then how do they relate with this? Again, what we were thinking is that, or what I was mentioning you is that, look, the R square, how well they correlate, this is a little bit larger or closer to 1 than this one. Now, I would like to plot in one, I will plot just all the historic data since 1970, and it's going to be this time series. I'm going to plot the using this whole period. I'm going to use this regression, and I'm going to use only this, the one that we just estimated as a linear regression. Okay. So let's do the following. Okay, I'm just copying again this. Okay. Here I'm just going to select data, and this I'm going to change it for historic data, the name. Okay. Then I'm going to add another one that it's going to be called whole period. The X values will be the years, and the Y values going to be the population. I'm going to start since 1970. Then I'm going to add another one that is going to be called 1970 2000. Again, the same X values. And then these are the Y values. Okay, so now we have here the three series that we were looking. Of course, this one doesn't look quite the same, but let's try it. Okay, so for this one, I'm just going to select it, right click, and then do format of the data series. Here in the marker options, I will change it to built-in, and then the triangle. So you can see that now the triangle has changed. I'm going to keep it here as 6 or 7. Then, yeah, this is for the whole period. This one that is here, this is the 1970. So here I'm going to select the one that is circular. I'm gonna select no fill, and the marker line color I will select black. Okay, so now this one looks a little bit more like that. Marker options, I will keep it as 8. And finally, I'm going to try to select the one that is the historic data. As you can see here, it may be a problem. So basically what you can do here, when you cannot see, I can actually not select this one. So we can go here to marker options and we can make it small enough. So when I'm here, I can select the other one. A different way of doing this. So you can select, but it's going to be a little bit difficult. Select one, and then with the arrows, move up or down. And you see that moving the arrows up and down, I'm actually switching the chart, the time series data that I'm selecting. Once I have selected this, I just right click and say format of the data series. Here in marker options, I will go to circular, marker fill, solid, and I will add black. Marker line color, no line. And then for this one, I will make it a little bit larger. Okay. So now as you can see, this looks a little bit more similar like this one that we're looking. If we actually here add the trend, the linear, and then here I just edit this line in the line style using, it's this one, no, it's this one. It looks very similar to the one that is on the exercise. Okay, so okay, so we have selected, we have created these three different charts. Once you have created this, these are the questions. Okay, to be turned in. A, the chart with the three data sets plotted. So you need to copy this one. When submitting your exercises, something that it will be good to do is, well, first create a new document. Once you have created a new document, the first thing is that let's do this. Let's start with your name. So what I did is just here double click in the header and say name, and in this case is my name. Then here, with just by clicking tab, I will go here and add the name of the class is ESM 121 Water Science and Management. Here I'll add the number of the exercise, and then here just this. Okay, so now I have a template. When I submit my assignment, I'll know we can use always this template, but I mean this will be a good way for us to keep track. Okay, so now coming back here to be turned in, please try to write down the in which section we are. We are in the section of population. Of this exercise, that's in the section that we are. Now here, what we're going to do is this. I just copy this, paste it here, and now here I need to okay, what do we need to turn in? Well, this chart of with the three data sets, and then what I want you to tell me here is describe these two regressions. How do we obtain it? And out of these two, which one will you select to estimate the project future population? Or do you use any criteria? Are you not using any criteria? Okay, now let's move on. coming back here. Now let's see if the equation, the regression that you have selected is okay. Let's estimate what is the average decadal growth. How do we do that? Well, first of all, here in this cell, we're going to be subtracting this decade population minus the previous one. And we can do the same for the rest of the decades. So as you can see, we get to the numbers that were here. We can do the same, and with this power regression, we can do the same, and we can also do the same with this linear regression. Okay. Now, once we have done this, let's estimate what is the average decadal growth for these equations. So here, we just type the average, and this is the average decadal growth, and this will be the average decadal growth for the other ones. Every time that I type F2, that's how it gets these cells colored. Okay, so notice that the average decadal growth, the historic, it was about 9100. With this equation, looks that this starts kind of the average over this period is about 9500. And this, because it's linear, it's adding up pretty much 9400. So as you can see, out of this, the linear, the estimation with the linear regression is the closest one to the historic, not as much as the whole period. So here we have this part. So to be turned in here. Discuss the average decadal growth in Watsonville. Why the average decadal growth is linear. So notice here that some of the historic, sometimes is 8, sometimes is 7. Well, this is almost 9,000, 7,500, then 13,000, then 7,000. So an average is 19. So do you think this is growing linear? Did you select the linear growth equation as your regression equation? So in this section, did you select linear or the one that it was the regression equation using the power regression? Was it necessary to estimate this decadal growth? Do you think we need to estimate it? Do you think we don't? If we estimate, once we have estimated this decadal growth, how does that calculation help you to support your decision in selecting either this regression equation or this regression equation? Did you make a more informed decision once you have known what is the average decadal growth or not? Okay, so we have estimated our population growth. Now let's save this, and we're going to save it as okay. Also make sure to save your Excel file. Okay, now we are on the water use per capita. As I mentioned before, here we have now estimated the population. Now we're going to estimate the water use per capita. Once we have these two, we're going to multiply them and estimate the future water demand. Okay? So how are we going to do this? Now you need to switch to this tab that is called water use per capita. And okay, what do we see here? These are the groundwater use and surface water use of Watsonville in acre feet per year. So 1 acre by, the acre is the area by 1 foot of depth. That is the volume that we're seeing here per year. And we have data since 1999 up to 2010. So we have all this data. We know how much water is used from surface water sources, which are these, and from groundwater sources. Okay? So the first thing that we're going to do is to try to estimate what is the water use per capita. First, we need to estimate the water use, and then if we know what is the water use annually and what is the population annually, then we can estimate how this water use per capita has changed throughout the time. Okay, so the first thing that we're going to do is to create a plot of this. So I'm going to select these two time series. I'm going to go here to insert column, and we need to have this as an stacked column graph. So now it's kind of start looking similar. Now let's do this. Here, just go right click, select data, and in this one we're going to select that the years. For series 1, we know that one is the groundwater. Series 1 is the water used from groundwater sources. We know that series number 2 is the one coming from surface water sources. Okay, we can actually type here only surface water, and then for this one we can type groundwater. Okay. So now this one, it does look more similar than the one that I'm asking on the exercise. To including the y-axis level, you just need to go here to layout, axis, primary vertical axis title, and then here, and just type per use, and then acre feet per year. Okay, so now we have a very similar chart. Now, the first thing that we are going to start doing is to add these two sources. So why this was good for? What I'm trying to show you here is that most of the water that is used by this city comes from groundwater sources, very few from surface water sources. So now let's add these two sources of water together by just clicking here, equal sum, and then selecting these two cells. Again, you just copy this cell and then paste it with Ctrl V here. Okay. So now, as you can see, we have the same values like the ones that I'm asking here. Now, we have just find the volume. This is the volume of water that we need. Well, the volume of water used by the city of Watsonville. This volume is in acre-feet per year. And usually the water use per capita is estimated as gallons per day per person. So in order to go from acre-feet per year to gallons per day, the first thing that we need to do using these conversion factors, so basically you can see here that 1 acre-feet is equal to, let me see, here, 1 acre-foot is equal to this much gallons, 325,851 gallons. So I'm gonna use this or this number and multiply it by 325,851. So now we, instead of having acre-feet per year, now we have gallons per year. Now we don't want gallons per year, we want gallons per day. So these are gallons per year. If we divide it by 365, we're going to obtain gallons per day. Now here, this is the we're using the same equation like this one, the linear regression equation that we use for population. In this case, what I'm going to do is to copy this. Instead of year, what I'm going to need is select, this is the year, and it's going to be minus that value. I'm just using again the same equation that I did to estimate the population. So this is the estimated population using the linear regression equation. Okay, so now I have the volume and the amount of people. How do I estimate the water use per capita? Well, I divide the volume in gallons per day divided by the number of people living in Watsonville during that year. So as you can see, this is 163 gallons per day. We can estimate that a person in Watsonville in 1999 used to it used 163 gallons per day. Now let's plot these values and see how they look like. And actually we're going to plot the water use per capita with the precipitation data that is here. So let's select these two. How can we select these two interactively? Well, basically what you can do is first select this data, and once you have selected, hold the key Control and then drag until you have selected also the precipitation. Once you have done that, then you just go here, insert, and we can do this column. Now in this case it doesn't look any similar like the one that we are trying to do here. First let's select this one Let's go here, right click and hit select data. Here the first thing that we need to know is that, or that we need to tell Excel is to declare that we are using as the x-axis the years here. Now the first series here, it's okay. So this series number 1 is the precipitation. So we put this as their name. And then the second one, the name is the water use per capita. Okay. Again, still, this one doesn't look the same as this one. Okay, the first thing is just select the bars, right click and go to format of the data series. Once you're there, go here and select here. Here, as you can see in series options, it's asking you that is in the primary axis. If you select secondary axis, it will go to a different one. Then we can also here do change series. We can select a line. So now we have something that is looking a little bit more similar. Let's do this. Okay. Okay, now we can actually see it a little bit better. Okay, now this, in order to change this one to this gray color, you can just go select it, right click and go to format of the data series, fill, let's select solid and this gray. For this, you just select it. For the other, for the line, just select it, go here to line color, solid line, and select black, like the one that is already here. And line style, let's go a little bit thicker, and then here selecting this time of dash type. Close. So as you can see now, it looks a little bit more similar of the one that I'm just presenting here. You can always go here to layout, and here in axis titles, you can select in the primary, so in the one that is on the left. Here, select and type water use per capita, and these are gallons per day per person. And then we can select exactly the same axis titles. Go here in secondary axis title, rotate it, and here we can type precipitation. Okay. And now we have the two types, the two y-axis titles. Okay, so this one kind of vanished. Let's just precipitation. Now we have it. Okay. So, what do we need here? Okay. What is the trend of the water use per capita in Watsonville? I mean, if we compare 1999 to 2010, what is the trend? What is the trend here? Do you see any pattern? Actually, isn't the water per capita not just kind of going down? I mean, consider that at the beginning it started at, what, about 160? Look, in 1999 it started at 163, and now in 2010 it's about 120. So now here is to be turned in. Now we are in this section. What do you use per capita? So the first thing that I'm going to ask you is to the plot chart when we have the water use per capita and the precipitation. Do you think that the water use per capita since 1999 has increased or decreased comparing to 2011? Take a look at this web page and see what are the free indoor conservation devices that the water agency in this area has been providing. Do you think this has something to do with the decrease in the water use per capita? So the water use per capita here is about 125 gallons, which is about 473 liters per day per person. How does this this water use that is about 470 liters per day per person compared to other nations? So look at this 473 might be somewhere in this neighbor. Look, what is the water use per capita of other nations? Are we using less water, more water than other nations? Why do you think? Okay, so let's go back here. And now let's start working. So this is only for the city of Watsonville, but there is also some rural communities in this area. Let's do the same procedure as we did before and try to first obtain the volume of water, in this case in gallons per day per person, like here. And then let's estimate the population as we did here, and then just divide the volume by the population. Okay, so in this case what we need to do is to add this water use, and in this case we only have data for 2010. So let's add these values for other municipal and rural and residential, which is this. This is the volume in acre feet per year. Now let's estimate this in gallons per year. And this will be my multiplying this times 325, 851. And then here it will be, this is per year, so we should divide it by 365 days, and we have it this per day. What is the total population, rural population? In this case is the sum of all these different cities throughout the coast. At the end, the water use per capita is dividing this many gallons by the population. Dividing this over this. Okay, so we have about 132 gallons per capita per person per day, gallons per day per person, which is actually, as you can see here, for the city of Watsonville is 120 that we saw here at the end. In 2010, they were using about 120 gallons per day per person. In the rural communities, they are using about 132. So in this case, to be turned in, I want you to discuss why the water use in the rural communities is a little bit higher than in the city. The city has to do something with leakages, with no meters. Do you think they are using more water in a specific use? And I don't know, in their lawn, in their cooking, in their washing things? Please elaborate on that. Do you think they have less sophisticated equipment and water-saving devices to supply water? What do you think is the difference between these 132 and gallons per day per person and this one, 120? Okay. Okay. Now don't forget to save it. And finally, we have the population and the water per capita. Now we're going to estimate the future water demand. Go to this projected water demand. So let's estimate the population with the linear regression equation that we have used before. So here, instead of the year, I'm going to select this. Okay. So it's 939.82 times the year minus 183. 7306.8. Okay, so we have estimated the population. Now, here for the water use per capita, we're going to use the value that we estimated before, which is 120. So you can just type equal, then go back here to water use per capita and select this value that we thought in 2010, and then click enter. And then here in the water use per capita, we're just basically going to use in liters per day this times the conversion factor. So we are using about 454 liters per day per person. Now let's estimate how much water we use. What is the water demand since 1970 up to 2050? So it's going to be, if this value, which is the population times the water use per capita. So now I'm going to click here F4, and you're going to see that this dollar sign starts appearing. So every time that I click F4, in this case appears 2, then just 1, and then just the other one. What does this mean? The $sign fixes the value in a cell, fix the cell. So in this case, if what it's saying is that it's going to be fixed C, which is the column, and then 3, which is the row. If this only has one sign, it will only fix, in this case, the row, but not the column. Or in this case, it will fix the row, the column, but not the row. So let's see if when I do this, and then I copy all of this, you can see that it's multiplying the population times the water use per capita. This value is moving vertically. This, because we fixed it with the $2 signs, is just staying there. Okay, so now we have estimated the water demand in gallons. Oh, and this is, okay, so this is the population times the water use per capita, the gallons per day per person. And we need to multiply this, so this is per day. We need to multiply it because we want to obtain the gallons per year times 365, which are 365 days. Okay, so now we have that value. And this is in gallons. We want to convert it now into acre feet, so it will be this value divided by the conversion factor, which is 325,851. And this has to be divided. So this is the projected water demand if, well, this is the projected population, and considering this water use per capita, this is the projected water demand for the city of Watsonville, considering a linear increase in the population. Now, let's think in a scenario that actually let's plot these values in a chart and see how do they look like. Again, right click, select data, and then here we select the years. Here, as the name, we're going to call it this only water demand, or let's call it current trend. Okay, and then we're going to plan for a scenario that actually will use the same amount of water before 2010, but it will only use, instead of 120, we're going to reduce it to 102 gallons per day. So a reduction of 15%. So for these years, we're going to use exactly the same water demand for this scenario. And then for these years, we're going to use population instead of using 120, we're going to use 102 gallons per day, and then times the 365 days in a year. In this case, in order to obtain this volume in acre-feet per year, we're just going to this volume divided by the conversion factor, which is 325 8 851. Once we have done this, let's just also plot this data. Okay, so here we use just this, and then for here we're going to use this one. Okay. Don't forget to hit Control to save it. Then once you're here, we're just gonna, instead of doing this, we're gonna select this as a line, and then I'm going to change this, the line color, to black, and the line style as this dash. So now it actually looks a little bit more similar like the one that I'm asking here. Okay, so to be turned in, what I want is to plot both of these water scenarios. Okay, I want you to submit the plot, this plot of the both water demand scenarios, and then to elaborate that this policy produced, I arbitrarily select 15%. What action will you propose to actually achieve this 50% reduction? Less consumptive toilets or harvesting water. What would you do to achieve this 15%? Okay, this is it for this first exercise. I hope you enjoy it. See you.